Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. Lecture 30 is on circles and polygons, or rather polygons and circles. We'll first talk about polygons. So last time we talked about triangles and quadrilaterals. Quadrilaterals had how many sides?
4.
Yes, quadrilaterals had 4 sides. The figure I'm showing you now has 5 sides, and it's called a pentagon. Very good. Pentagon. You can count the sides. 1, 2, 3, 4, 5 sides. Makes it a pentagon. You've probably heard of the Pentagon building in Washington, D.C. That's where the military's top brass is stationed. They do all their decision making from there. And that shape is the shape of a pentagon. If you look at the building, that's what it looks like. It looks like a big pentagon. All right, the next shape that I'll show you is called a hexagon. And a hexagon has, let's count them, 1, 2, 3, 4, 5, 6 sides. So a 6-sided shape we call a hexagon. What if the shape has 7 sides? What do we call that? Anyone have a guess? Probably not. It's a tough one. A heptagon has 7 sides. 1, 2, 3, 4, 5, 6, 7. Heptagon. Now this next shape you're probably very familiar with. If you've paid attention to street signs before, it's the shape of the American stop sign. And it is called an octagon. And it has how many sides? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. 8 sides. Octagon. I might have mentioned that September, the sept in September, that's kind of related to the hept in heptagon. Like the Latin version is septagon, I guess you could call it. The Greek prefix would be heptagon. That means 7, and September used to be the 7th month before July and August were added, the Roman emperor months. And October would have been originally the 8th month. After the octagon comes a 9-sided shape called a nonagon. Sometimes you'll see it referred to as an aneagon, but nonagon is more standard. And you can count the sides. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sides. The last one I'm going to show you is a 10-sided shape called a decagon. So let's go ahead and count the sides of this shape. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sides. That's the decagon. December, deca, used to be the 10th month before the 2 middle months were added. Now it's the 12th month. Decade, you're probably familiar with the word decade. That's a 10-year span. The decathlon is a 10-event Olympic game. And decimal, our decimal number system, the deci part, same prefix, meaning 10. We, of course, have a base 10 system built out of 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes? Let's look back at the pentagon one more time. You'll notice that all of the side lengths are the same, so it's equilateral, and all of the angles are the same, so it's equiangular. And when this is the case, we call it a regular pentagon. All the shapes that I've shown you so far are regular polygons, meaning that they're equiangular and equilateral. But they don't have to be that way. All right, so let me give you a chance to try and identify some shapes. So what you'll do is you'll count the sides and then try to identify the shape based on that. And also tell me whether it's a regular polygon or not. If it's not a regular polygon, it's irregular polygon, okay? Or you can just say not regular. That's fine too, I suppose. So pause the video. Come back when you have your answer. Okay, who identified this as a hexagon? It's got 1, 2, 3, 4, 5, 6 sides. making it a hexagon. They appear to all have the same side length and the same angles, making it a regular polygon. Let's try another. Actually, the example that I have is not quite as crazy as I would like, so let me draw one instead. There we go. That's a crazy looking shape, huh? So go ahead and try to identify this shape, count the number of sides on it, and identify whether it's regular or not. So pause the video, come back when you have your answer. Okay, you want to count the sides for me?
1, 2, 3, 4, 5, 6, 7.
7. So that would make it a heptagon? Heptagon. Now, is it a regular heptagon? No, it's not. Look, this is a very short side. This is a really long side, so this is a very irregular shape. But it is a heptagon because it has 7 sides, but it's not a regular heptagon. Okay? I did have an example I would show on the screen, but you might at first think it was regular because it wasn't all that irregular. Right, you guys probably remember that with triangles we had a rule about the internal angles of the triangle, yes? What was the total angle inside the triangle? Does anyone remember?
180.
180, exactly. So just like the triangle, there is a rule for the internal angle on a polygon, and the rule is that the total angle, I'll call it total internal angle, is equal to the number of sides minus 2 times 180 degrees. So for a hexagon, for example, we would have 6 sides. So here's a hexagon. We would have 6 sides. So that means that L is equal to 6. So we have 6 minus 2 times 180 degrees. What is 6 minus 2?
4.
So this is 4 times 180 degrees. And 180 times 2 would be, we could do a long multiplication if you like. 180 times 4. 8 times 4 is 32. Carry the 3. 4 times 1 is 4. Plus 3 is 7. 720 degrees. Alternatively, you could have simply doubled 180 twice. If we double 18, we get 36. If we double 36, we get 72. And then the extra 0 makes it 720. Yeah? Okay. Let me let you try one. What is the total internal angle inside of a pentagon? That's the 5-sided shape. So go ahead and pause the video. Come back when you have your answer. Okay, the pentagon, L, is equal to 5. That gives me 5 minus 2 times 180 degrees. 5 minus 2, of course, is 3. And 180 times 3. 8 times 3 is 24. Carry the 2. 3 times 1 is 3, plus 2 is 5. And so we get that the total internal angle inside of a pentagon is 540 degrees. Now you may have noticed that the decagon is starting to look a little bit circle-like, right? As we add more sides to a regular polygon, it starts to look more and more like a circle. If we have an infinite number of sides, then that essentially is a circle. But that's not how we define the circle. A circle is defined as the set of points that are a fixed distance from a specified center. And that sounds kind of funny to say, but let's see. I think I can show a way to see it. If you tie a piece of string to a pen, and then you simply fix, that's going to be tricky here. You fix the end of the string at some point, trying to draw not a huge circle. And then just allow yourself to rotate around like so. Something like that. Not terrible, but it's not great. So by fixing the string and tacking it down here at the center, right, I'm able to create a set of points that are equidistant from this center point. And we call this distance from the center point, the radius. Radius comes from a Latin word meaning wheel spoke. And so you can think of your bicycle wheel, the spokes in the wheel, those are little radii. And so that's where the word radius comes from. And that is this distance. Wherever I draw a line from the center, it's going to be the same. And that basically is what makes a circle a circle. Related to the radius is the diameter, which is equal to 2 times the radius. And the diameter would be any line that you can draw that passes through the center of the circle. It will be equal to the diameter or twice the radius. What about the perimeter of this circle? This has a special name too. And the circumference is basically just the perimeter. Circum, the prefix in circumference, means to go around. It's another Latin prefix. Another tool you can use to make a circle, and I think I have one right here, is a compass. A compass is a very handy tool. This is a very good compass because you can control the radius. If I take a piece of paper, I can create circles like this. There, see? I don't know if you'll be able to see that on the camera or not because it's not that dark, but yes, compass. Very handy for making circles. If I take the circumference of a circle and I divide it by the diameter, this is an old observation. I think even like the Babylonians or the Sumerians had observed this, though they didn't really get the number very accurate. But the ratio of the circumference to the diameter of any circle is a very special number. Let me see if I can write the number a little better. Does anyone recognize that symbol? Seen it before maybe? It's a Greek letter. It's the Greek letter pi. And this is the symbol we use for the number pi. Why is this number special? Now, approximately, you'll want an approximation for this, right? And so this number is approximately, you could write it as 3.14. That's an okay approximation. If you wanted a rational number that approximates pi, 22/7 is a good choice. Okay? It was Archimedes that found that pi was less than 22/7 and greater than, I think it's 223/71. Yeah. He found that it was somewhere in between here. So if we decimal approximate these, we would get, this would be 3.140845. 22/7. Does anyone remember how to divide 22 by 7? Let's do that real quick. That's a good exercise. So you'll probably recall that when you divide by 7, it's not so nice. So if I divide by 2, that's usually pretty easy to do. Like 1 divided by 2 is 0.5, and then a repetition of zeros forever. But whenever I divide 7 into 22, 7 times 3 is 21, leaving a remainder of 1. Drop down to 0. How many 7s go into 10? Well, we can get 1. And 10 minus 7 is 3. Drop down another 0. How many 7s go into 30? 7 times something is pretty close to 30. Anybody? 4. So we get 4. Gosh, and that's a 28. That leaves a remainder of 2. Drop down to 0. How many 7s can go into 20? 2. Leaving 6 left over. How many 7s can go into 60? 8. What is 7 times 8? 56. How many 7s go into 40? 5. Drop down another 0. How many 7s go into 50? 7. That's going to leave 1 left over. But remember, we already had 1 left over up here, so it's just going to repeat again, right? So we're going to repeat this 142,857 over and over and over again and again and again, right? And that's kind of characteristic of a rational number, is that it has some set of digits that it just repeats over and over again. Oftentimes it's just a 0, like 0.5, 0.50, and then 0 repeats. Sometimes it's a single digit, like 1/3. 1 divided by 3 is 0.3 repeating. Yes? Just 0.3333333, right? When you divide by 1 by 7, it's a repetition. 142,857, 142,857, 12848, etc., etc., forever. And that would be what we would write here. 3.140857. 0.142857. And so pi is somewhere in between here. Of course, today we can calculate it very accurately, not using any methods that I can discuss with you today, but, and pi, the first several digits of pi is something like, I'll have to write this down. It's going to be 3.141592653. And if I do the dot, 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 I guess it's okay to write equals there. Normally you would write approximate if you chopped it off somewhere, if you truncated it or rounded it. So you can see that our 22 over 7, or 3.142857, is accurate to about here, right? So it's equivalent to using 3.14 for pi, essentially. So I can use this observation that the circumference divided by the diameter is approximate or is equal to pi. It's exactly equal to pi, by the way. And I'm going to use that to come up with a formula for the circumference. And what I'm going to do is I'm going to multiply both sides of this equation, circumference over diameter and the constant pi on the right-hand side, by diameter. If I do it over here, I'll get a cancellation. Diameter, I'm going to represent that by d times c over d. You'll see that because we have a diameter in the numerator and a diameter in the denominator, that they're just going to cancel. And I'll just be left with the circumference. And that'll be equal to pi times the diameter. Okay? Since these cancel, I can erase them. And that leaves just the circumference on the left-hand side. And more commonly, people, what they do is instead of writing the diameter, they write it in terms of the radius. And remember that the radius is related to the diameter in that the diameter is just 2 times the radius. So this is more commonly written as c for circumference equals 2 pi times the radius r. The 2 and the r, that's the diameter. And the pi is there because of this observation that the circumference divided by the diameter is equal to pi. So using this formula, the circumference is equal to 2 pi times the radius, you can calculate the distance around any circle if I give you the radius. Make sense? Now, you can approximate your answer using either 3.14 for pi or using 22 over 7 for pi. Yeah? Or you can give your answer in terms of pi. So for example, if I said, what is the circumference of a circle of radius 1? Well, you'd substitute in 1 for the radius of the circle, and then you just multiply that times 2 pi. And so I'd say the answer is 2 pi. If it's 1 meter, it's 2 pi meters. If I wanted to know what a real distance was, because maybe I have to measure something out, perhaps I'm going to get a piece of string to tie around some large circular object, and I've measured that this thing's radius is, I don't know, 10 centimeters. To figure out how much string I need, and I'm going to measure it with a ruler, presumably, I could do something like this. I could say, okay, I've got that r equals 10 centimeters, or inches if you want to use inches. The circumference would be 2 pi times 10, which is just 20 times pi, which I can approximate as 20 times 22 over 7. 22 times 10 would be 220. 22 times 20 would be the double of that, or 440. So this is equal to 440 divided by 7. I can do the long division on that. How many 7s go into 44? 6, giving me 42. That leaves me a difference of 2. Drop down to 0. How many 7s can I get into 20? 2. 14 is almost enough, right? But not quite. Leaving me 6 left over. How many 7s can I get into 60? 8. Leaving a remainder of 56. Gives me 4. So that's enough for now. We'll say that this is approximately 62.8. And my answer, of course, would be centimeters if I was using centimeters, or inches if I was using inches. Since I was using centimeters, I'll write it. So that would be the distance around that circle. Let me point out that this is the basis for another kind of measurement of angle. So you're familiar with the degrees, where 360 degrees is all the way around. if I consider this to be a unit circle, meaning that the radius is equal to 1, r equals 1, then the distance around is 2 pi. And so what we do is we say that 2 pi radians is equal to 360 degrees. So it's just a different way to measure angle. And it's called radians. You'll see that a lot in higher mathematics courses, especially in trigonometry and calculus and stuff like that. Not so much in algebra, but... And it's just based on this circumference formula, right? So the distance around a unit circle, that is a circle with radius 1, is 2 pi, and we call them radians. And you should think of them exactly the same way you think of degrees, except that all the way around, instead of being 360, is 2 times pi, okay? Which is a little more than 6, but that's not the important thing. So you can, if I wanted to say, what's 180 degrees? Well, half of 360 is 180. So what's half of 2 pi radians? What's half of 2 pi? What is 2 pi divided by 2? It's just pi radians. Pi radians is equal to 180 degrees. If I take half of that again, 90 degrees, I get 90 degrees. So tell me what 90 degrees is in radians. So pause the video, try that, come back when you have your answer. Well, since all I had to do was take half of 180 to get 90 here on the right-hand side, I'll do the same thing on the left-hand side and take half of pi. And we call it pi over 2. Pi over 2 radians. Normally people don't write the radians part. They would just write pi over 2 equals 90 degrees. But that is one way to measure angle, is in radians. And it's related to the circumference, or the distance around a unit circle. All right, the one thing that we're kind of missing here, right, is area. The area of a circle. And again, this is not something that you can easily just come up with. Like, remember, when we got the area of a triangle, we did it by considering the area of a square. So if I had a square, I know the area for that. It's just the length times the height, right? Or the length squared, right? For a triangle, all I need to do is just take half of that. Here's a triangle, you see? So it's 1/2. Call it A times B. A times B, right? That's how we figured out the area for a triangle. But how can we figure out the area for a circle? And it turns out that we can do something rather interesting. If you can imagine inscribing a bunch of little triangles all pointing towards this center. This is what it would look like if you drew quite a few of them. See? Just putting a lot of triangles. The smaller the triangles you make, the better it's going to fill up that circle, right? But you need more triangles. Here there's not so many. It looks like maybe 20 triangles or something, right? And if I take those triangles, and I imagine kind of unrolling the wheel, right? Unrolling the circle and laying these out flat, then this is what the triangles would look like. The length down here on the bottom would be equal to the circumference, whereas the length of this leg of the triangle here would be the radius. You see? Now I can imagine leaning these triangles over on themselves and stretching them out a bit, right, without changing their actual area. And what we end up seeing is something that is basically a triangle, yeah? Now, if I use more and more of these triangles, in the end, that triangle that we get from these triangles inside the circle will end up looking like a right triangle, where this leg is equal to the circumference, and the height is just the radius. And the formula for a triangle, the area of a triangle, you'll recall, is 1/2 the base times the height. But here we have the circumference times the radius, which I'm going to write as C times R. We have a formula for the circumference already, yes? It was 2 pi times the radius. So I'm going to substitute that in. So the area of our circle, 1/2 circumference times radius, that's the same thing as 1/2. Replace circumference with 2 pi times the radius. 2 pi times the radius, but times the radius again, right? Because we already had the radius in our area calculation. These 2's will cancel, and I end up with pi times r times r, well, that's r squared, isn't it? And so we get the famous formula, pi r squared, which you can actually derive by considering triangles. Isn't that funny? So let me ask you to use this formula, pi r squared. You can either use 3.14 or 22 over 7 for pi. And I would like you to answer the following question. Have you ever played that game at maybe camp or in school where you have this parachute and you flop it up like this and the kids run under it? It's basically a big cloth circle, right? And you wave it up and everybody holds a piece of it and they form a circle, right? Now, if I bought one of these little parachutes and its radius was, let's say, 7 feet. So 7-foot radius. My question is, will this fit in a room that's 12 by 12? So we have a rectangular or a square room that's 12 by 12. And I want to know, can you fit this parachute whose radius is 7 feet in this room? Okay? Well, there's not just one way to solve this problem, so I want you to try whichever way you're most comfortable with. Pause the video, come back when you have your answer. Okay, so how do we figure this out? Well, there's a couple of ways. I'm going to draw a mock-up of my room here. This is 12 feet by 12 feet. And I said that the parachute that I'm getting, the big circle, is 7-foot radius, which means its diameter is what? 2 times that? 14 feet, right? So I can imagine from, say, the center of this room, if I tried to fit, if I drew a circle such that the distance across the circle was 14 feet, would it fit inside this 12 by 12 room? Well, since clearly 14 feet is going to extend out bigger, right? Here's the 14 feet. Or excuse me, here's the 14 feet. Yeah, it's going 1 foot over on each side, yeah? So it's too big for the room, so that's not going to work. Another way to do it would be to calculate the area, and the area of the room and the area of the circle. That should give you some idea on whether you can imagine covering the whole floor of the room with the circle, the area of the circle. If the room was big enough, then you ought to be able to get it to fit. Now you may have to distort it a bit, but you know. So what would the area of this room be? Well, the area of a square is just the length squared. So the area of the room, which I'll write as area of a square, is equal to 12 squared, which is equal to 144. In what feet squared, meters squared, whatever the units are that you're using. What about the area of the circle? Well, the area of the circle is going to be this number pi, which we'll write as maybe 22. Well, we haven't done decimal, so let's do decimal this time. 3.14 times, the radius was, I said it was 14 or 7? 7. 7 squared. That's the same thing as 3.14 times 49. And so over here I can work that out. Remember how to do this multiplication? 3.14 times 49. 9 times 4? Work for me. What is 9 times 4?
36.
Okay, carry the 3. What 9 times 1 is? 9 plus 3 is? Someone else maybe? 9 plus 3? 12. Carry the 1. 9 times 3?
27.
27 plus 1? 27 plus 1? 25, 26, 27, 20. Yes, 28. Good. 28. That takes care of the 9. Don't forget the 0. 4 times 4. Let me erase my carries. 4 times 4?
16.
16. Carry the 1. 4 times 1 is 4 plus 1. 4 plus 1? 3, 4,
5.
5. Good. And finally, 4 times 3?
12.
Good. 12. Let's add all these up. That's a 6. 6 plus 2 is 8. 8 plus 5. Oh, that's a tough one. What is 8 plus 5? I forget.
13.
13. Carry the 1. 2 plus 2. Does anyone know 2 plus 2? 4. Plus another is 5. And then 1 over here. And we have 1, 2 decimal places. So put the decimal right there. So we get that the area here is, hopefully I got this right. All those pauses may have wreaked mischief on my problem here. 153.86, which is decidedly more than 144. So I've got a couple of different ways to say, no, this parachute is not going to fit inside this room. We'll have to get a smaller parachute if we want to play that game. Okay? I think that is all I have for you. That was polygons and circles. Can anyone here tell me what 2 plus 2 is? How about you? 2 plus 2? Very nice. Okay, so I honestly, I forget what next lecture is on. Does anyone know? Lecture 21 is basic statistics, huh? Okay, so the next lecture, basic statistics. That's what it'll be then. So I'll see you then.